Today we're going to talk about bonding, so how atoms stick to each other basically, and mainly covalent bonding. So covalent bonds are shared electrons between two nonmetal atoms, so this only has to deal with nonmetals, and they are created by trying to achieve an octet, which is a word that we've talked about in the past. So oct means 8. So every atom is always trying to get 8 electrons around it, so it has a full octet. And every bond consists of 2 total electrons. There's a few things that don't need a full octet, and we'll talk about that in a little bit. So Lewis structures are a way to represent compounds on a piece of paper instead of in 3D. So all of these will be flat structures. And Lewis structures only represent covalently bonded compounds or molecules. There are no metals in Lewis structures ever. So the difference between ionic and covalent things, remember, is ionic compounds always have a metal. That'll be a good review for later on this year as well. So just keep that in mind. If it has a metal in it, you're not going to draw a Lewis structure for it. Lewis structures only show valence electrons. And remember, these are the same as group A numbers on your periodic table. So if you don't have your periodic table out, go ahead and get that out. You're going to want it for the rest of this lesson. It's really important. So you can pause the video here if you need to and get that out. Electrons are grouped in pairs for Lewis structures. And I'll show you what that looks like with some examples. Find lithium on the periodic table and notice that it's in group 1A. And that means that lithium has 1 valence electron. So we're going to represent that electron with a little dot. So just draw a dot right next to lithium. Now find chlorine on the right side of the periodic table. Chlorine's in group 7A. So chlorine's going to have 7 total electrons. And the way I want you to draw them around the atom is first we're going to put 4 electrons down. Make 4 dots. 1, 2, 3, 4. Then they're going to start to pair up. So it's a total of 7. We'll have 5, 6, 7. So you should have 7 around. This one has no pair. It's just an electron by itself. Okay, we'll try one more with oxygen. So oxygen is in group 6A. So he'll have 1, 2, 3, 4, 5, 6 electrons. And you'll notice these two are both unpaired and they want to stay that way. If electrons can be by themselves, they kind of like it better that way, because they're both negative and they want to stay as far apart from each other as possible. So pause the video here and I'd like you to try the rest of the atoms listed on the page. So sulfur, boron, and carbon. Alright, let's see how you did. Sulfur is right below oxygen, so it's going to look identical to oxygen. So if you fill in that structure, you'll notice that. And sulfur has some very similar bonding properties with oxygen. It's going to be it's going to do some things that are in common. Boron just has 3 electrons, so they will not be in pairs. You're just going to put them around boron by themselves. And carbon is the most versatile atom on Earth. It can bond with so many different things because it has 4 electrons. They're all unpaired. It's like having a Lego with 4 little spots where other atoms can come in and stick to carbon. You and I are made completely of compounds that have carbon in them for this reason. Now we're going to talk about the directions for how to draw Lewis structures for molecules. So the very first thing you're going to do is to find the sum of the valence electrons from all the atoms in the compound. So go ahead and look at the examples that are listed below this box. There's a whole bunch of them, and the first thing we're going to do is find all of their valence electrons. The first thing you're going to do is count up the total number of valence electrons. So the first thing is find your first atom. Find your first atom and find out how many valence electrons it has. So carbon has a total of 4, plus You're going to have 4 hydrogens, so it's going to be 4 times the amount of valence electrons hydrogen has, which is 1. And that's going to be a total of 8. You'll notice that it's a multiple of 8, obviously, so that's what we're kind of shooting for here. Then you're going to put carbon in the center because it's listed first. It's also the least electronegative. You're going to put carbon in the center, and then you're going to put the hydrogens around the outside. So typically, the atom that you want in the center is the one that's listed first. Okay, I want you to do the same thing with the rest of these molecules. Find their total number of valence electrons, and then arrange the atoms without any bonds yet. Just arrange the atoms so that all of the atoms are as far apart from each other as they can be around the central atom. Pause the video here. Okay, let's see how you did. Again, carbon has 4. Plus 4 times 7 will be a total of 32, because bromine has 7 valence electrons. So we'll put these all around the outside, as far apart from each other as they can possibly get. Nitrogen has 5 plus 3 times 1. It's a total of 8. Once again, nitrogen will be in the middle, and this time, since you only have 3, you're going to spread those hydrogens as far apart from each other as they can be, and that'll be in the shape of a triangle. So go ahead and do that. Change the shape. If you made it kind of more like a T, you need to make it in a triangle shape like this. Boron has 3 valence electrons, plus fluorine is 3 times 7, so this will be a total of 24, which is also divisible by 8. Put boron in the center and fluorines around the outside. So all of these atoms that are just kind of flailing around out here, they all have to have at least one bond. So draw one straight line between each of the atoms. So draw one straight line between each of the atoms, and that will represent your bond. I don't know if I'm going to be able to do this very well. So each one of these is 2 electrons. And if you count up your bonds here, that's a total of 2, 4, 6, 8. So this one's completely done. Okay, for carbon tetrabromide, we're going to do the same thing. So start with 4 bonds, linking all of the atoms together. So you've used 8 total electrons so far out of the 32. So what we need to do is go back through and add electrons onto all these bromines. So we've counted 2, 4, 6, 8. And we're going to start in pairs around the bromines. 10, 12, 14, 16, and I haven't really left myself enough room here, but we'll try to weasel them in. 18, 20, whoops, 22, 24, 26, 28, 30, 32. So now if you notice, every single atom has 8 electrons around it. Some of them are shared between carbon and bromine, but this one has 2, 4, 6, 8 around it, and the carbon has 2, 4, 6, 8 around it. So usually you're aiming for symmetry because those electrons want to spread out as far apart from each other as they possibly can. Alright, let's do another one. This time we're shooting for 8 total electrons with NH3. This is ammonia. So you'll notice this time it's a little different. You've got only 3 things around the outside. So we're just going to put in 3 bonds. So that's 2, 4, 6. But we're supposed to put 8 electrons in this molecule, so we have 2 extras left over. The hydrogens can only support 2 little electrons. Hydrogens are small and they can only hold 2. So we're going to put those 2 extra electrons on nitrogen. 1, 2. Now I want you to go ahead and label this. We haven't labeled it before, but this is called a lone pair. Sounds like an oxymoron, but it's a pair by itself. Maybe put a little circle around this so you remember. That is a lone pair. And this one has tons of lone pairs on it. Okay, pause the video and see if you can figure out what to do with boron trifluoride. Okay, let's see how you did. This time you have 24 electrons to deal with. So we're always going to first start with simple bonds. 1, 2, 3. So that takes care of 3 total. That takes care of 6 total. And then all of these fluorines, you know how much fluorine loves electrons. It's going to have electrons around it as well. So we'll do 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And boron doesn't have an octet. He's only got 6, but that's okay. Boron's okay with that because he's a really, really small atom. I want to draw your attention back to these rules about how to draw Lewis structures for molecules. I went through all of them and the examples, but we didn't go through them step by step. So it's important that you read through them. And look at the exceptions for small atoms down at the bottom. So hydrogen only needs 2 total electrons around it. That means 1 bond. And boron and beryllium can accept less than an octet. So they don't have to have 8 things or 8 electrons around them because they're just too small to even handle that. They can't accept all those electrons. Go ahead and flip over to the back of your paper. Okay, here are a few more examples. We'll start with water, most common substance. So first, find valence electrons. Hydrogen has 1 valence electron, but there are 2 of them. So we'll do 2 times 1 plus 6 for oxygen, and we get 8 total. Now the rule I've told you is that the first atom is usually the central atom. But in this case, hydrogen is just too small to be the central atom, and there's also 2 of them. So in this particular case, we're going to put oxygen in the middle and put 2 hydrogens off to the side and connect them with at least 1 bond. Hydrogen can actually only hold 1 bond, so that'll be it for the hydrogens. So there's 2, 4, but we need a total of 8 electrons. So think about where you might put those extra electrons. They can't go in the hydrogen because they can't accept anymore. Hydrogens will never have lone pairs. So we're going to put the remaining electrons, 2, 4, 6, 8, around this oxygen. So you have a total of 8 around the oxygen. Each hydrogen only has 2, that's all it needs. Okay, let's try carbon dioxide. Carbon has 4, plus there's 2 oxygens, and each one of those has 6. So 2 times 6 is 12, plus 4 is 16 total electrons. For carbon dioxide, you have carbon listed first, so you're going to put carbon in the middle. And you're going to put the 2 oxygens off to the side with at least 1 bond. Okay, so you have a total of 16 to deal with here. So think about who likes electrons more, oxygen or carbon. That'll kind of help you deal with this. So this is a strange situation. I want you to actually just put your pencil down for a second and watch me do this. So we're going to give everybody all the lone pairs they could want. So there's 2, 4, 6, 8, 10, 12, 14, 16. You can see we're already starting to run into a problem. 18, 20. This is an issue. We can't have this. Now, everybody has an octet, which is what they want, but we have way too many electrons spread out over here. We can only use 16. So think about what we could do to solve this problem. Instead of having them all spread out like this, we're actually going to have some sharing of electrons going on and some extra bonding, or it's called a double bond. So we're going to take away electrons from both the carbon and one of these oxygens. So take these two away, take these two away, and you're going to make a double bond. That's just another bond that goes right in here, if I can get it to work. Okay, so now we have 2, 4, 6, 8, 10, 12, 14, 16, 18. That's still too many. We're going to do the exact same thing on the other side. So we're going to take another pair of electrons away from carbon and another pair away from oxygen, and we're going to put in a double bond. 2, 4, 6, 8, 10, 12, 14, 16, and hey, what do you know? That's the right amount. One little note I want you to write on here: double bonds are stronger than single bonds. Carbon dioxide is an extremely stable compound for this reason, and that's why we have problems with it as a greenhouse gas, because these bonds are so difficult to break, and they also, this compound stays around the atmosphere for a long time. Let's try something a little more complicated. This is called ethane, and there's 2 carbons and 6 hydrogens. So we're going to follow our same process. 2 times 4. This carbon has 4 valence electrons, plus 6 times 1. So that's 8 plus another 6 is 14. So the structure for this one, it's actually got 2 central atoms. And if you ever take organic chemistry, this is something you'll see a lot. So carbon forms the backbone of most compounds that are used in biology, and you may have even seen some of this last year, although you may not have known what it is yet. So we're going to bond these 2 carbons together with 1 bond, so that's worth 2 electrons. Then I'm just going to sprinkle the hydrogens around the carbons. Remember, hydrogens can only have 1 bond, so you can't stick hydrogens to other hydrogens in a chain. It just won't work. So now we have 2. We're going to put in some more bonds. 4, 6, 8, 10, 12, 14, and that is ethane. I don't really expect you to remember that, but she'll probably see it again in the future. Okay, we have almost the exact same compound here down at the bottom, but instead of having 6 hydrogens, we only have 4. So this time you're going to take 2 times 4 plus 4 times 1. You're going to set it up the exact same way. 2 carbons in the center. Put your hydrogens around. But this time we only have 4, so I'm going to space them out like this to try to get all the hydrogens as far away from each other as we can. So this is going to be a total of 2 times 4 is 8, plus 4 is 12. So 1 bond in the center. So 2, 4, 6, 8, 10. We have 2 more electrons to deal with. And if you notice, these 2 carbons here don't have a full octet. Right now they only have 2, 4, 6, 2, 4, 6 on each side. So we're going to solve that problem by putting a double bond right there. Now he's got a different name. It's called ethene. So we know small atoms like hydrogen can only accept 1 bond, but bigger atoms have more valence shells and can accept more bonds than just 4. So they can have more than an octet. And expanded valence shells are observed only for nonmetal elements in period 3 and beyond. I'll show you what that looks like on a periodic table. So on your periodic table, this is period 3, and anything from phosphorus on, that's a nonmetal, can accept expanded valence. Remember, the noble gases don't really bond, but strangely enough, we can actually get krypton and xenon to bond. So if you want to make a list of the ones that will do this on your paper, anything below row 3 that's considered to be a nonmetal can accept expanded valence. So let's take a look at a few examples of expanded valence. Phosphorus has 5 valence electrons plus 5 times 7. So that's going to be a total of 40 valence electrons. So think about who's going to go in the middle in this compound. And the least electronegative is phosphorus, so it's going to go right in the middle. Then you want to spread out all those chlorines around the outside. So 1, 2, 3, 4, 5. All right, let's draw one bond between each. 1, 2, 3, 4, 5 bonds. So that's 2, 4, 6, 8, 10 electrons that we've used up so far. So we have 30 left to go. So here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. Everything's spread out. Everybody has an octet. Phosphorus has more than an octet, so phosphorus is the one with expanded valence. So if you want to make yourself a little note of that, you can. Alright, I'd like you to pause the video here and try the structure for sulfur hexafluoride. Sulfur has 6 plus 6 times 7, and that's a total of 48. Sulfur will go in the middle. Now you guys know a lot about fluorine and how stingy he is with sharing electrons. He's just not going to do it. So you can't string any fluorines together here. They all have to hang off of the sulfur. So we're going to make 6, 1, 2, 3, 4, 5, 6, as far apart from each other as you can. Put your little fluorines in there. We have a lot of electrons to distribute this time, but hopefully you can start to see the pattern where these electrons go. So we've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, and you're all done. Sulfur has expanded valence. Okay, this one's a little bit strange because xenon is a noble gas, but fluorine is actually able to bond with xenon because xenon is such a large atom and fluorine is so small and so electronegative that he can take his electrons or share them. So xenon has 8 valence electrons, very, very uncommon for it to bond. Plus 4 times 7. So you'll have a total of 36 electrons in this case. Xenon will go in the middle. Spread out the fluorines. Okay, so we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We've used 32. we actually have 2 extra sets of electrons to put around here somewhere. So we're going to do that on the xenon. So you'll have 2 extra electrons here and here. Doesn't really matter where you put them, you can put them any place. But xenon has 2 extra, what do we call these little guys? Lone pairs of electrons. Okay, you'll use the same rules to draw structures for polyatomic ions. In addition to those rules, if an ion has a negative charge, like almost all the polyatomic ions, you're going to add that negative charge to the total number of valence electrons, and I'll show you what that means with an example. If the ion has a positive charge, you will subtract that number from the total amount of valence electrons. Because remember, if it has a positive charge, it actually has a less total electrons. Then we're going to draw brackets around the structure. We're going to indicate the charge on the upper right hand side of the brackets. That's where the charge will go, right in this little area. Here are some common examples of polyatomic ions. This is sulfate. Let's just write the name so we don't forget. So sulfur and oxygen are actually in the same column, and they both have 6 valence electrons. So this will be 6 plus 4 times 6. Then here's the difference right here. This overall has a -2 charge. You're actually going to add another electron to this whole structure. So 6 plus 4 times 6 is 24. Plus 6 is 30, plus another 2 is 32 electrons, which is divisible by 8, which is easy. So we're going to put sulfur in the middle. Oxygens will go around the outside. You know they're going to be bonded at least once, so we might as well just put that in there. So we've used up 2, 4, 6, 8. Time to sprinkle some electrons. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and that's our total. The only thing that makes this different, besides the charge, is when you have an ion, you need to put the whole entire thing in brackets to mean this whole structure is included. You're going to put the charge of the ion on the outside. So this is going to be 2 minus for the whole structure. I want you to try the same thing for ammonium. Pause the video here and give it a try. Okay, nitrogen has 5 valence electrons plus 4 times 1 for hydrogen. This gives us 9 electrons, but remember, it's got a 1 plus charge. If it's positive, it actually means it's lost electrons, which are negative. So you're going to subtract that 1 back out of the system, so you get a total of 8 yet again. Nitrogen goes in the middle. Hydrogen's around the outside. Remember, hydrogens are only allowed to have 1 bond and no lone pairs. So look, 8 electrons, 2, 4, 6, 8, a piece of cake. Total of plus 1 charge for everything in the brackets. Let's see how much you remember from polyatomic ions. Pause the video and give each one of these their proper name. Okay, if you said nitrate and cyanide, you were right. Nitrate has an overall -1 charge. Nitrogen contributes 5 plus 3 times 6 minus 1 means it's got an extra electron in there, so we're going to add that in. So you really have 6 plus another 3 times 6, which is 24. Nitrogen goes in the middle. You have 3 atoms around it, so let's spread those out evenly. We'll need at least 1 bond between each. 2, 4, 6. Now, you may not want to draw this quite yet from here on. Just watch what I do. 24 total. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Seems okay, except we have a problem. Nitrogen in the middle here doesn't have an octet. He only has 6 electrons around. So remember when we solved that problem the last time, we had to make a double bond. So it doesn't matter which oxygen you take those electrons from. It makes no difference at all. I'm just going to pick the top one. And I'm going to take 2 electrons off of that and share it with the nitrogen. Now it really doesn't matter. In fact, this has something called a resonance structure, which we'll talk about in the future if you take AP Chemistry. But now we have 2, 4, 6, 8 around this oxygen, 8 around this one, 8 around this one, and 8 electrons around the nitrogen. You can go ahead and draw this. The whole thing will have a charge of -1. Pause the video here if you need to draw your structure. Okay, if you have 2 atoms, there's no central atom, so you put them right next to each other. So carbon has 4 plus nitrogen has 5, plus it has an extra electron in there for a total of 10. Put them right next to each other, C and N. Now, we're going to sprinkle our electrons. Again, you might want to watch me do this first. 2, 4, 6, 8, 10, 12, 14. 14? That's way too many. We only have 10 to deal with. Time to start pairing up. So let's take some electrons from each side and make a double bond. 2, 4, 6, 8, 10, 12. Still too many. Let's share another pair. 2, 4, 6, 8, 10. Here is the structure of a very poisonous chemical, cyanide. And the reason cyanide is so dangerous is it actually looks very similar to another chemical, which is really important in your body. You don't need to draw this, but this is what oxygen looks like. And these end up in the same place in your blood, which is why cyanide is so toxic, because it knocks out the oxygen.